Okay, so far in chapter 4, we've focused on reactions of two solids. So we've thought about grams of A reacting with grams of B, and we've made a solid. Now, in this part of the chapter, what we're going to say is we're not just going to think about two solids reacting with each other, because it's actually kind of rare that we're able to do reactions like that. Most of the time what we do is we make solutions. And these two solutions will react with each other and give us some sort of product. And the reason why we use solutions is because we have better control over how things react, and we also don't have to use as much stuff because it will react easier when it is able to find, the reactants are able to find each other in the solution. So we have to think about what is a solution, what are the components, and how do we think about the quantities that we report in a solution. So a solution is a homogeneous mixture of two substances. So whenever we make the mixture, we're always taking a solute and we're dissolving it in a solvent. Okay, so that's also how you know. It's a solution of something dissolved in the solvent. So the solute is the thing that we have less of. It's the minor component. So this is the stuff that is being dissolved. So it's getting mixed into the solvent, which is the thing that you have more of. And this is the stuff doing the dissolving. In this class, we're going to focus a lot on water being our solvent. Water is a great solvent because it's cheap, it's easy to get, and a lot of the things that we talk about in this chapter dissolve well in water. And so when we're thinking about water being the solvent, so if water is the solvent, we use a new state of matter to describe it. So we say the state is aqueous, and we give it the symbol AQ. So this means that whatever substance we're assigning the AQ symbol, that thing is dissolved in water. So for example, if you dissolved some sugar in water to make simple syrup, then we would put the formula of sugar or sucrose, and after it we would write AQ because it's still sucrose, it just happens to be dissolved in the water. We make solutions all the time, right? We make sugar water for simple syrup, we make salt water when we're doing cooking, all these kinds of things. Another solution you might be thinking of is coffee or tea or lemonade. All of these things are homogeneous solutions of our solute dissolved in our solvent. When we're thinking about chemistry though, and we want to do some reactions, we have to have a way to actually communicate how much stuff we dissolved in our solvent to make the solution, because we want to be able to do reactions and still do stoichiometry to predict how much product we should make, but we don't have grams written anywhere. Instead, we use a concentration unit known as molarity. So when we're talking about concentration, this is the amount of solute in the solution. Molarity is the most common way we report that, although it's not the only way, and we'll talk more about different units of concentration in chapter 13. But for right now, what I want you to know is that concentration is going to mean molarity in this chapter. So what is molarity? Well, molarity is the moles of our solute divided by the volume of solution. And this volume of solution has units of liters. Okay, so again, molarity has units of moles per liter. And what I really want you to understand, and so I'm going to put a big star by this, is that if you have a volume in liters and you want to get to the moles, or if you have moles of something and you want to get to the liters, the conversion factor between them is molarity. So just like before, when we used molar mass to get from grams to moles and vice versa, now we're going to use molarity as a way to get between volume and moles. So let's talk about how to calculate the molarity of a solution. So this says we want to think about what the molarity is when we added 45.4 grams of sodium nitrate to a flask and dissolving with water, so that tells us that water is the solvent, to a total volume of 2.50 liters. So we're looking for the molarity. So molarity is the moles of solute, so in this case our solute is sodium nitrate, over the liters of solution. So if we're given the grams of sodium nitrate, we know that grams can go to moles really easily using the molar mass. Sorry, this is a bit messy, so I'm just going to rewrite it. 45.4 grams of sodium nitrate. We're going to convert to moles using the molar mass, which is 84.99 grams. And we'll divide by the solution volume, which was given to us as 2.50 liters. And so the molarity of the solution is 0.214 molar sodium nitrate, which means that we have 0.214 moles of sodium nitrate per 1 liter of solution. And so I want you to think about molarity being a really nice conversion factor. Okay, molarity, the most important thing I can say, and I've said this already, but I'm going to say it again because that's how important it is. Molarity allows us to convert between moles and volume in units of liters. So if you see something like X molar solution, what that should mean to you is that we have X moles per 1 liter. And as you know, with all the other conversion factors we use, we can rewrite this as 1 liter over X moles, depending on what we're trying to solve for. And so we will do this in not on the next page, but after that. And so just keep this in mind as we go through. But before we do talk about how to do reactions with molarity, we have to talk about dilutions. Why do we want to talk about dilutions? Well, a lot of the time what happens is when you buy a solution for lab that you do a reaction with, they sell it to you in a very concentrated way. So a stock solution is a way to store or ship solutions. But in order to save money, right, these are usually sold as a concentrated solution because it's very expensive to ship a giant container of water, right? And so instead, they'll sell you something that's concentrated, meaning that we have lots of moles in a small volume. And you know that this is the case, right? So like if you ever use bleach, you wouldn't use the straight bleach out of the container. You always dilute it before you use it because otherwise it's too concentrated. Or if you go to do laundry and you use a little pod thing, those pods are very, very concentrated so that you don't have to use a cup of detergent. Or if you use vinegar, right? Usually you don't use the vinegar straight out of the bottle, you dilute it first. So in fact, we do household dilutions all the time. We just don't think about it. But we're going to talk about dilution because this is something we do a lot in the laboratory. So when we're talking about dilutions, essentially what we're doing is we're going to prepare a less concentrated solution. So when we're solving for the molarity, what that says is that our new molarity is smaller. It's going to be a lesser value. So what happens is the number of moles stays the same. But because you're changing the volume, the molarity changes. So the volume changes, so the concentration changes. So when you see the word diluted or dilute or something about a smaller concentration, there's a formula that we use for this. And that formula is C1V1 equals C2V2. You might also see it as M1V1 equals M2V2 because the concentration unit is molarity. But let's look at what this all means. So if you know the molarity of your stock solution, so this is the molarity of our more concentrated solution, and you know the volume of the stock solution, then you'll know something about what the new concentration is going to be. So C2 is the molarity of your diluted solution, and the volume, V2, is the volume of your diluted solution. So notice they have to be paired up. And again, you will know when to use this equation if it says the word dilution in the problem or if it says something just about concentration changing. And while we're here, let's talk about the units. So the C1 and C2 have units of molarity. V1 and V2 have units of liters. But because the conversion for liter to milliliter is multiplied and the equation is multiplied, you can also use milliliters for volume as long as V1 and V2 are both in the same units. Okay? So as long as both are the same. So they can both be in mils, both be in liters, but don't use different units for each. Okay, so let's do an example for a dilution. It says sulfuric acid is typically sold as an 18 molar solution. How much 18 molar sulfuric should you use to make 100 mils of 0.375 molar solution? And so what you see in this problem is there's no reaction, no equation, and so we know because the concentration changes, it has to be a dilution problem. Usually in a dilution problem, it's going to say the word dilute in it. This one doesn't happen to. Okay, but we can still see that because the concentration changes, we know that this is a dilution problem. Not changes, decreases. So let's think about what's going on. Okay, so we know that our starting concentration is 18 molar. We know that our starting volume, well, actually, we don't know the starting volume, so we need to figure out how much of it we need. We know that our ending concentration is 0.375 molar. And we know that our ending volume is 100 mils. So that means that the units for V1 will also be in milliliters. So let's apply our equation. C1V1 equals C2V2. C1 is 18 molar. V1 is what we're solving for. C2 is 0.375 molar, and V2 is 100 milliliters. So if you multiply 0.375 by 100 and divide by 18, we get that we need 2.1 milliliters of the 18 molar H2SO4 to make this solution. So we really don't need very much at all in order to make the solution. And if you're trying to like picture what it is that's going on here, essentially you'd have a large container of H2SO4, which is the 18 molar, and basically you'd take a tiny amount of it, which is that 2.1 milliliters, and add it to a 100 milliliter container. So we would add 100 mils, well, not a 100 milliliter container, 100 milliliter volumetric flask. Okay, and then we're filling it with water up to the line that's marked on the flask. And so by the time we're done making this solution, instead of having 18 molar for our concentration, whoopsie daisies, go away, the new concentration in here is going to be 0.375 molar. So basically we diluted it with a bunch of water so that our molarity is now a lot less. Okay, so we've talked about how we define what molarity is and that we can use molarity to convert between moles and volume. We've talked about doing dilutions. Now let's use our ideas that we know from the first part of the chapter to think about a theoretical yield. But now, instead of only using grams, we are going to combine ideas and think about how we use molarity and the yield. So molarity combined with doing a theoretical yield problem. Okay, so this says how many milliliters, so we're looking for a volume, of a 0.150 molar HNO3 solution are needed to completely react with an aqueous solution of 0.450 grams of sodium carbonate to form sodium nitrate, carbon dioxide, and water. The first thing we're going to do is write our balanced equation. So we're reacting HNO3, and we'll learn soon that all acids are aqueous, and also because it says it's a solution, you know we're going to put the AQ symbol. It's going to react with sodium carbonate. So we know sodium is Na+, carbonate is CO3 2-, so the formula is Na2CO3. That's also aqueous. To form sodium nitrate, so sodium is Na+, nitrate is NO3-, so we're going to do NaNO3. That's AQ, and we'll learn later in the chapter why. And then we have CO2. I'm just going to rewrite this because I ran out of space. Sorry. Na2CO3. And we're making sodium nitrate and carbon dioxide, which we know is a gas, and the other product we're making is water. And now, and I'm sorry, that L is very ugly. Water is a liquid, which we know. Okay, so now what we're going to do is we have to balance this equation. So we have 2 sodium on the left, so we're going to put 2 on the right. We have 2 nitrates on the right, so we need 2 on the left. That gave us 2 H's. We have 2 H's, 1 C, O, and O, that's 3 O's, so that's right here. So notice I balanced nitrate as a group because it made it a lot easier to pay attention to where my different things were going. So it made it easier to track the O's when I was able to keep the O's from the polyatomic together versus the O's from the rest of the problem. Okay, so let's think about what's going on here. The first thing we're going to do is figure out how many moles of sodium carbonate we need. How do we do that? Well, we have the molarity. Oh, I'm sorry. That's crazy. We have the molarity of the HNO3. For the sodium carbonate, what we have is 0.450 grams of it. We need the moles, So we're going to use the molar mass. Okay? So the molar mass of sodium carbonate is 105.99 grams per mole. All right? Then, well, you know what? I'm going to rewrite this because I'm not sure in which order we're going to need it. So I'm just going to write 105.99 grams per mole because we'll use it however we need it. Now, in order for us to go from the moles of sodium carbonate to moles of nitric acid, we know that we have to use the mole ratio from the balanced equation. So what do we have at this point? Well, we have the moles of Na2CO3 from step 1 or step 2. What do we need? We need the moles of the HNO3. So we have to use the mole ratio from the balanced equation. So far, this problem is exactly like every other theoretical yield problem we've done, where we figure out how much of the thing we have, we figure out how much of what the mole ratio is, and then we solve for the moles of the other thing. So in this case, it's not actually a theoretical yield problem, it's a how much of the other reactant problem, just like we did in class on Monday. So the last part, normally, once we have the moles of the thing we're interested in, we go to grams using the molar mass. In this case, we're not going to do that because we have a solution of the nitric acid. And so it doesn't make sense to try to find grams when you have a solution with a certain concentration. So instead of using the molar mass like we typically would in the last step, instead what we're going to do is convert to a volume using the molarity. So if we have the moles of HNO3, which we just found from step 3, what we need is the volume of HNO3, and we know that what we're going to use is the molarity, which is 0.150 molar of our solution, because molarity converts from moles to volume and volume to moles. So let's put all of this information together and write it in a combined step, the same way that we were doing earlier in this chapter. So we start with our 0.450 grams of the sodium carbonate. Now we're going to do step 2, which is we're going to use the molar mass of sodium carbonate to get the moles. Now we're going to do step 3. We're going to go from moles of sodium carbonate to moles of nitric acid using the mole ratio. Oops, did something weird to my formula up there. So 2 moles of HNO3 for every 1 mole of sodium carbonate. And now the last step here, so we finished step 2, step 3, and now step 4 is going to be to use the molarity, which is 0.15 molar. But we want to know a volume. So we're going to write 1 liter, 0.15 moles of HNO3. So right here, we're using the molarity, which is step 4. But notice I wrote the liter on top because we're interested in a volume. And notice how we're able to cancel all of our units except for the volume, which is what we're looking for. So if we do all the work in this calculation, we get 0.0566 liters of HNO3. The question asked us for milliliters, so now we'll do our prefix multiplier. 1 mil is 10 to the minus 3 liters. Oops! So we get 56.6 mils of the HNO3 is what we need. So notice, just like we did earlier in the chapter, we used the molar mass first, we used the mole ratio. Normally, we would use the molar mass again, but we don't want a molar mass because we have a solution, so here we used the molarity. And that's how this problem was different than what we've done before. But again, not tricky, right? Because the strategy is always the same. And so it's just a matter of practicing until you remember that we always need to get to moles of a thing first so that we can use a mole ratio. And then the last step is just conforming to what units the problem asks us for. So we're going to talk about a specific type of this kind of reaction. But I think we'll pause here because I think that that's a lot to process. And then I'm going to give you a problem similar to this to do for your check-in.